Hey there. I'm going to be showcasing my implementation of the shortest path algorithm. For our simulation, we first need to create a class for our graph. This way we can actually, have our nodes on our vertices. Um, this class, it's a pretty straightforward. The most important functions are the add edge, which allows us to add nodes and their value, add their nodes and their edges between them, and the weight value between the edges. The other one is get neighbors, so we can see how our vertices are connected, which ones are neighbors, which one are directly connected to them, and get vertices, which gives us a list of all the vertices that we have in our graph. We got a couple of extra functions. These are just a couple of remove functions to help me work with the graph, make our life a little bit easier, and then a copy function that just allows me to copy the function into a new graph. And these are going to be used just to make my life a little bit easier while working on this simulation. Um, Once we got that, we got our example showcasing how the graph works. We got an initialization of graph for G, and then we add our edges. AB, A to B with the weight of 5, A to C tree, C to D 1, D E tree. Um, we add all of these, and now we got a little graph work. Then I can print out the neighbors of vertex A, and it's going to be in this case B and C, and you can clearly see it's B and C. And then vertices in the graph where you can get all the vertices, and they're going to be A, B, C, D, E, E. As you can see, that's all of them in our little example. Now, now's the big part, the A star implementation. Um, we got two functions here because A star needs a little extra helper function called reconstruct path at the end of it. This just in in fast terms, it's just a little function that tries to recreate the path given came from using current. So it'll go through came from and it'll keep getting nodes. Gonna I'll explain it a little bit more in detail as we learn more about the A star implementation. So my A star implementation takes in four parameters. In theory, this could have been hard coded to only take two, just our start and goal. And H and graph could have been ignored, but I wanted to make it complete, so we got all four parameters as it's typically used. A star, the first parameter is their start. That's where we're starting, you know, where we're gonna begin our search for our goal. Our goal is where we want to get to. H is going to be a heuristic function. In our case, my heuristic function, I define it a little bit later, but it's going to be, we're going to be using the weights. And then we got graph. I use this to work with our H function. Once we got these parameters, we need to initialize a couple of values. We need to initialize an open set. This is going to be all the nodes that we are aware of, that we have discovered. This set is going to slowly grow and shrink over time as we learn about our graph and its properties. Came from is going to be it's going to keep a list of the best way to get from a node from start to that node, and what node came right before that our node that we're interested in. G score is going to be a list that contains the value for all of our functions. This value it's gonna be initially infinite, and as we learn about our graph, it's gonna keep changing. It's trying to figure out what's the cheapest path towards a node, if from start to a node n, for example. To start, the the cheapest path to start is zero. It's gonna be zero because yeah, it the fastest way to get from start to start, it's gonna be to start, so it's gonna be zero. We got the F score. This is gonna keep track of our heuristic values. At the start, it's initialized as infinite. It'll change. For our start, we're gonna have our heuristic value. Um, this the we'll talk about the function later, but this is just a value that it's what we what do we value? What do we consider important in our path? For different implementations of A star, we're gonna use different ways of calculating H. Different, be it maps, be it video games, be it different other programs, technologies, projects, they're going to have different heuristics. This is what we value in that project, what we want to use as our way of getting the shortest path, or our the path with the most value for us. Now that we got that set, we initialize. We're gonna be stuck here in our while loop of the open set. We're gonna be stuck here for a while. Opens. We're gonna be interested in getting from the open set the verdicts with the lowest F score. Once we get that, we'll initialize current and declare it as that value. This is going to be important. We want the lowest F score because that's an indication that this is the cheapest, the best way to go through. If we find that current is equal to goal, then we're done. We're done and we can get out of the while loop. We can leave and just use the reconstruct path and return the path that we took to get from start to our goal. Sadly, this isn't going to be the case most times. So once we get our current and we realize that it's not our goal, we're going to remove it from the open set. We're going to now analyze its neighbors and their weights. So we're going to get the neighbors of that current node and their weight. Once we get that, we're going to give each neighbor a tentative G-score that is going to be the G-score of the the removed current node plus the weight of that neighbor. This way, we're basically keeping a track of how much it costs to get from start to here, as including the current value. This will keep on increasing. Now, if we find that our tentative G-score is less than the G-score that the neighbor already has, then we're interested in this path because it means that this path is good. It's cheap. It's the shortest path. It's got the best value, the best bang for our buck. Because we're interested, once we realize that hey, this path is good, we're gonna do a couple of things. In our came from set, we're gonna say that hey, the current node, that's the best way to get here to our neighbor. So the best way to if we're coming from current is to go to neighbor. Like the best way to neighbor came from is current. Now, we also want to give our G-score, the neighbor, this G-score because we found that hey, this is a really good value. So we now know that hey, this is our G-score. This is gonna be what we're gonna want to find values lower than this. Then our F-score, we're gonna get our tentative G-score plus the heuristic function that we're using. This is gonna give us another idea. And then we're gonna add our neighbor to the open set if it's not in the open set already. If it's already in the open set, we don't need to add it if that's the case, but if not, we're gonna add it. Then That with that we just expanded the open set. Now we're gonna grab. We're gonna have a couple values here in open set once we finish this for loop. A couple of extra nodes, and then we're gonna do the all again and again and again until eventually, hopefully, we're gonna find goal as our current set, as our current node. If this fails, this means that we went to every node and we couldn't find anything connecting the start to our goal. Therefore, the best thing to do, or well, the only thing we can really do, is return a failure. We failed. We couldn't complete the task. With that, the A star is implemented. This is all that we need for A star. It's a pretty straightforward piece of code. It's neat and it's versatile. Due to the heuristic function, we can really use it for a lot of stuff. You can use the heuristic function to value certain stuff over other. Now, once we're done with the A star implementation. We got our reconstruct path. We need to define our heuristic function. Before that, I wanted to have a little more visualization in our Jupyter notebooks. So I made this little cell that, well, let me run that cell just in case. I made this little cell which uses networks and matplotlib. This is only using it to visualize our graphs. This is a way so we can see our graphs. Here we got positions for all values of graphs, so they can be positioned best and just made pretty. It's just a code to make stuff look pretty. It's a little bit of sugar on top of our little simulation. Now's the big thing. We need to set up our graph. Our graph, here it is, as defined in the project. Here are all the edges with all the values, and we can just run it, and we get a pretty similar looking graph. Using visualize graph, we can get a pretty similar. It's a little bit different. All the values are going to be the same. All values have been checked, and they are good. Good. So this is what the graph would look. Our graph is going to look. It's going to have all the values and everything's implemented. It's great. It's perfect. Now, once we have this graph, now we can look for shortest paths in these from one node to another. We can check if from California 1 to Illinois, California 1 to Michigan, Texas to Washington. We can find every path that we want. But before that, we do need to declare our heuristic function. The heuristic function, I just used the edge weight. This is the thing that we value in this shortest path. We only care about the edge weight, the weight of the edges. For other practical implementations, there's going to be different ways of defining our heuristic depending on what we actually value, what we want to have on our score. But for us, it's just going to be the edge weight. This little function just gets the weight between neighbors, and if we find that we have a state that the second state is declared, we'll just return the weight. Now we're going to find our paths here. These are going to be the three paths as the project wanted us to simulate. It's going to be New York to California 2, Washington to Georgia, and California 1 to New Jersey. These paths are gonna be reconstructed here, and we're gonna have it. Once we run this node, we now have our paths set up. Now we want to visualize them. This little node just visualizes them. It makes a copy of the original graph and then removes all the nodes except the nodes in the path, the nodes that we care about, and then we're gonna visualize. You can already see here that we got all the nodes. I also have this little node here, just making sure that's got the original network, so we can compare. We can see New York to California 2. It goes to Texas, Georgia, Pennsylvania, and then New York. This is a valid path, and it does pretty seems to be pretty much better by just another path we could have taken would have been New York, Pennsylvania, Illinois, and not sure which state this is, but this is gonna be 750, which is the same as Georgia, but it's gonna be better here between Illinois and New and E than between Georgia and Texas. But once we get to NE, then we got 600 again, 600 again. This is already like a lot, and then we're gonna have to 750 to California 1 and then California 2. All this adds up. It's way more than our than 1,800. So it's pretty straightforward path. Same for Washington to Georgia. It goes to Illinois, Pennsylvania, Georgia. Even if we take the other path, it just get other paths like Washington, California 1, California 2, Texas. Just here, this is between California 2 to Georgia. It's basically the same as Washington to Illinois. Even worse, in fact. Yeah, it's even worse. And yeah, with this, we can clearly see these three shortest paths. In theory, we can actually make a couple more for any node that we want if we wanted to. If we wanted to, for example, let's grab this and let's, I don't know. We got, how about UT, from UT to New York. Oh, New Jersey. Let's see, New Jersey. New Jersey, and then we can visualize this graph. It's going to be, we're also going to need this little code. You also need to define just a little couple codes. This is going to be the copy of G. This is from G, UT to New Jersey. We're going to remove the nodes to, let's just path UT, New York, and then we can just visualize this UT, New York, New Jersey. Once we run this, yeah, it goes from UT to Michigan to NG. Yeah, we can use this for whichever path we really want. It's really useful. A-star algorithm is really good algorithm. It's versatile because of the heuristic function, and it's pretty commonly used a lot in video games, especially in roguelikes, as a way to know the best way to get an object to another, the best pathfinding for enemies or for NPCs or whatnot. Yeah, that will be Project Tree. I hope you have a wonderful night or day, and take care. Goodbye.